Hello, class. Today's lesson is on Einstein's special theory of relativity. This is a special concept as it explains the behavior of fast traveling particles, and fast traveling unstable particles appear to decay more slowly than identical particles traveling more slowly. So, when we talk about nuclear physics and radioactive decay, it is noteworthy to look at Einstein's special relativity and it has been tested time and time again and without any discrepancies turning up. So it is a very important concept, an indispensable tool of modern physics. And when we are looking at any concept in modern physics, including radioactive decay and nuclear physics, in medical physics, special relativity is an important concept to look at. So let's take a look at the effects of special relativity. And this is one of the ideas that were part of Einstein's Annus Mirabilis in 1905. Albert Einstein released four major groundbreaking papers, and most scientists would be fortunate enough if they release one in their lifetime, and Albert Einstein released four. And those papers were discussed in a video in this post. Right now, we're going to focus on special relativity and the effects of special relativity. So basically, the three things that happen when particles travel at a very high speed um, is that there is time dilation, there is length contraction, and mass increase. I'm just going to quickly look at classical mechanics. In classical mechanics or classical relativity, we look at, let's say you have a person that is riding a bus, and let's say the bus is traveling at 60 kilometers per hour going in that direction. This person started to walk towards the front of the bus at 2 meters per second. Now you have an observer here standing on the ground at rest and looking at the person that is walking towards the front of the bus. To the perspective of the person looking here from the ground, this person is really traveling at 2 meters per second plus the 60 kilometers per hour. And just to make that the same unit, this is, I'm just going to round it off to 17 meters per second. So the person standing on the ground that is not moving relative to the bus and the person in the bus, the person in the bus is actually moving at 2 meters per second plus the speed of the bus at 17 meters per second. The person is perceived in the bus to be moving at 19 meters per second as perceived by the person on the ground. But if you were sitting here, you would see this person walking towards the front of the bus moving at 2 meters per second because this person is also moving at 60 kilometers per hour, 17 meters per second, the same as this person who is initially moving at also 60 kilometers per hour, but now started moving at 2 meters per second. Now, if you look at now light, let's take a look at light. If you have a person, this person on the bus, same thing, shining light to the front of the bus at speed of light. Now, C, Celeritas, is traveling at 3 times 10 to the power of 8 meters per second. And now let's imagine the bus to be also moving at C. So for the person on the ground, according to classical mechanics, the person inside the bus is emitting light at C plus C. Would this be traveling at 2C? No, according to special relativity, light is always traveling at a constant speed of 3 times 10 meters per second. This is a special case with light as it is always traveling at c. So that's one thing that we need to establish when we talk about special relativity. So light is a special case as it behaves differently than any other objects in classical relativity. So one thing that we need to make sure we consider is that motion is relative. And that is one of the things that we need to remember when dealing with relativity and physics in general. So in my next post, I'm going to cover the special relativity effects of time dilation, length contraction, and mass increase. And we'll be deriving the equations for those three. Okay.